Hi everyone. There's a big part of math that's devoted just to proving that things are true or showing that they are not true. Often when we're working with geometric properties, we're asked to prove that a property is true for whichever example we're given, or to prove that it's not true. That is to say, we are going to verify whether it's true or not. In order to do so with the lines and shapes that we're looking at, we need to know some basic properties that will link what we're trying to show with some kind of numerical values that will prove that it is so. Now these proofs can be done in other ways besides doing the calculations and showing numerically that they're true, but the numerical tools, the analytic geometry, is what we're going to be using mostly in this unit. For example, one thing that you might be asked to verify or prove would be verify that two lines meet at 90 degrees or at a right angle, right? And we know that if two lines are going to intersect somewhere and they're going to meet, then we know that it's a right angle between them, and we know from last year that we could show this by calculating the slopes of our two lines. We have a slope of this line, I'll just call it the slope of line 1, we have the slope of line 2, and whatever they equal, we know that they should be, if we're going to show that they're perpendicular to each other, that M1 is perpendicular to M2 if the slopes are negative reciprocals of each other. Right? So for example, if M1 was 1/4, looks something like that, then M2 would have to be, of course, -4/1 or -4. Right? We've done this a bunch of times. One other way of saying this is we could say if M1 times M2 equals -1, which is always going to be what you get if you multiply two negative reciprocals times each other, then M1 is perpendicular to M2. Right? So that's a common one, being asked to show that something is a 90-degree angle or perpendicular, and we know that we can do that by showing that the slopes are negative reciprocals of each other. Of course, we know very similarly that if we were to show that, if we were to verify that two lines were parallel, right, we know that our line 1 over here and line 2 over here, that if the slope of line 1 equals the slope of line 2, then they are parallel. Right? We've known that for a while, right? That the two vertical lines are the symbol for parallel. Right? Another common one. Show that two lines are parallel, and you can verify that by showing that the slopes are the same. Other properties can be demonstrated by calculating lengths. For example, lengths of sides. If you needed to show, for example, that a figure that was made by joining 4 points was a square, there's a couple different ways you could do it, but one way you could do it would be to say, well, I'm going to calculate the length of AB, the length of BC, the length of CD, and the length of AD. And of course, you know that in a square, all 4 sides are the same length. And you would say, if they are all equal, so if the length of AB equals the length of BC equals the length of CD equals the length of AD, then ABCD is a square. Right? Now you might ask yourself, do I have to actually prove that all 4 of them are the same length? If just 2 of them were the same length, could there be a possible other shape that it could be? Coming up with an example that disproves it would be called coming up with a counter example. For example, if I was asked, I've shown that length in my square, that length AB equals length BC. Is that enough to prove that this is a square? And I might say, well, maybe, but here's my counter example. Here is A, B, and C, and I might just draw D over here and say, no. Here's an example, a counterexample that proves that that particular one can't be true. So looks like I must have to I must have at least 3 lengths the same to make this or to prove that this is a square. So maybe you just wonder to yourself, I wonder if I can just prove that 3 lengths are the same. As well, I'm hoping that perhaps you might consider, if I prove that a couple of these angles, for example, are right angles. We just talked about maybe calculating slopes and showing that 1 or 2 or 3 or 4 of these angles are right angles. Then this might be a square. Would that be enough to prove that it's a square? Maybe we want to prove that some opposite sides here are parallel, right? Would that be enough to prove that this is a square? So these are all things that we could calculate. We could calculate slopes. We can calculate lengths of lines. And some of that information might be enough to prove that what we're trying to verify is true. Here's an example of something we might be asked to do. With or without the drawing, we might be asked to verify that ABCD, the figure formed by ABCD, is a parallelogram. I always think it's a great idea to draw a quick sketch of whatever you're looking at, but this one's provided for us, so we'll start working with this, and we'll decide how can we verify that this figure is a parallelogram? Well, I would have to say that I know something is a parallelogram if it has, parallelograms have 2 pairs of parallel sides, right? I know that AB must be parallel to CD. I know that AD must be parallel to BC, right? I also know that parallelograms have 2 opposite sides that are the same length. So I know that we have 2 pairs of sides with equal lengths. Now, as a side note, the question is perhaps, what if this was a rectangle? Would it still be a parallelogram? And the answer is that actually, yes, it would. So rectangles are included in in all things that are parallelograms. So rectangles are a smaller set of all things that are parallelograms, and for that matter, within rectangles are a special kind of rectangle called a square. So you can prove something's a parallelogram. You would have to maybe take another step to prove that it's a rectangle. That's just a bit of an aside. How are we going to go ahead and prove that ABCD that we have here is a parallelogram? Well, we could start by demonstrating that there's at least one pair of parallel sides. I think we mentioned that parallel sides can be proven by finding slopes, so I'll just find the slope perhaps of AB, and it looks like it would be 8 minus 5 over 0 minus negative 7, looks like 3 over 7, and the slope of CD, the opposite side, looks like it would be 5 minus 2 over 4 minus negative 3, 3 over 7. So I have found that the slope of AB equals the slope of CD, therefore AB is parallel to CD. Have I done enough? Have I proven? If I've proven that 2 sides are parallel, does that show that this must be a parallelogram, or do I have to show the other 2? I would point out that there are such things like, trapezoids, where 2 sides are parallel, but the other 2 sides are not. So I don't think I've done enough. I might also want to prove that the slope of AD, and check that against the slope of BC. Here we go, AD. D is the y value is 2 minus 5 over the x value is negative 3 minus negative 7. That's negative 3. I missed a minus there. Negative 3 plus 7 would be 4, so we have a slope of negative 3 over 4. BC is 5 minus 8 over 4 minus 0. It looks like I get negative 3 over 4. So the slope of AD equals the slope of BC, therefore AD is parallel to CD. Have I done enough? Have I proven that this is a parallelogram? I think proving that 2 pairs of parallel sides existing is proof enough for a parallelogram. So I could say, because I would make one final statement and say, therefore, because we have two pairs of parallel sides. A, B, C, D is a parallelogram. So that's one way that I could show that this is a parallelogram. I think there's more than one way. I think that I could go back and prove prove a different way that this is a parallelogram. I could go the route of going back and finding the opposite lengths of each side. I could talk about the length of AD compared to the length of BC, and then compare that to the length of AB and the length of DC. And I think if I had that, showed that two pairs of sides had equal lengths, that would prove it's a parallelogram. I'm just going to try this. I'm going to keep what I've got here. I'm going to keep that that I have one pair of parallel sides. And I'm going to actually check the length of those sides. So I'm going to actually see what the length of AB is and what the length of CD is. Right? So big formula, AB. So plugging into my formula, I've got I'm looking at AB, so 8 minus 5 squared plus 0 minus negative 7 squared. What's that? 3 squared plus 7 squared. 3 squared is 9, 7 squared is 49. I think I put those together, I get root 58. Let me check CD here. That's the square root of 5 minus 2 squared plus 4 minus negative 3 squared. I'm just noticing now that I'm doing my y's before my x's, but it doesn't matter in the length formula. What's that? 3 squared, and hey, look, another 7 squared. Looks like I'm going to get root 58. Right? I'm just leaving it as exact values. I could figure out what the approximate values. So, just using my conclusions about the slopes and lengths, I would say that because, here's my big therefore statement, because AB is parallel to CD and the length of AB equals the length of CD, this is a parallelogram. Is it? Do I have enough? If I have two pairs of parallel lines that are the same length. I haven't said anything about line AD. I haven't said anything about side BC. I challenge you to think about it. Is there any way that I could have two pairs of lines that are parallel in the same length and this not be a parallelogram? I think I've done enough. Maybe not. Maybe I haven't. I could do more. Like I said, I could find more lengths. I could find more slopes and prove beyond a shadow of a doubt that this is a parallelogram. But what I've done here, two different methods, just using slopes, but also using slopes and lengths. I've verified twice that this is a parallelogram. So here's something that you were asked to prove to show that this triangle given is an isosceles triangle. I would expect you to do a quick sketch of it and demonstrate that this must be an isosceles triangle.